And the second thing is that a lot of things which I will be talking today, we already went through in the first 2 days. And I will be focusing only on stuff which is completely new. So therefore, I will be asking you, or indicating the places where you need to go through the procedure similar to what we've done before, but I will not be going through that now. I will ask you to do it in your spare time, if you have that spare time. Okay? So, also, there were a few questions were asked about exams, so-called exams, so during the break. So, let's do the following. I just tell you that you should not stress out about that, and that's what I say today. But about the details, let's talk about that tomorrow. So I will, one thing I tell you for sure, that whatever I will be talking about on Friday obviously will not go into some sort of testing. It's just too quick. And the other thing is, of course, that 5 days is not enough to study anything properly. So therefore, for me, the exam or the test, whatever it is, it's just a formality. So it is something which we need to go through, and this is something which would demonstrate to me how much you understood, or just qualitatively, essentially, from what I had to say. And the good thing about that is that I will get some sort of feedback. This way is the best feedback I can get, because I will know for sure that whatever I did correctly, it's of course will be reflected by your exam papers, and whatever I did not quite well, obviously I will see that from the exam. So it is primarily for my own purposes, so don't stress out about that. And I'll talk more about this tomorrow. Okay, can we start? Yeah. Okay, let's start with new material. So, and as I mentioned to you, there are a few pages in my notes which describe qualitatively how the equations for describing the flow of viscous fluid can be derived, and what is needed to be there. So what new things need to be introduced. So I gave you a very brief physical insight in what is changing. More details are in my notes, and the bottom line is that equations that we have to solve to compute anything related to viscous fluid flow will be given by as shown here. And you can see that the left-hand side of this set of equations is exactly the same as in Euler equations. So this part is exactly the same, gradient of pressure is exactly the same, but on the right-hand side we have a whole lot of extra terms. And these are appearing because of the introduction of stress tensors. So viscous stress. The coefficient mu which we introduce here is experimental coefficient measured for individual fluids. So there is a special science which is called tribology, which deals with measuring these properties of fluid. So therefore it is pretty much experimentally given, so we cannot compute it. We have to take it from experiments. And in mathematical modeling, of course, we will just assume that it is known. It is given to us by experimental physicists. So from mathematical point of view, there is a huge difference between Euler equations, which we considered previously, and this set of equations that are known as Navier-Stokes equations. So just addition of these extra terms makes a huge difference. So what do you think? Why am I saying that the addition of these terms makes a huge difference? What actually happens mathematically when we add these terms? So that's right. So you see, whatever terms we had before, they had derivatives of the first order. Time derivative and space derivatives, they all were first order. Here we have second order derivatives. So equation has a higher order of high order derivatives, second order derivatives. How many boundary conditions are required? So you actually need to count the number of derivatives. So if you take U equation, right, the first equation, you see that I have second derivative in x, second derivative in y, second derivative in z for U alone. So U function alone has to have 6 equations specifying what happens at the boundary. 6 for each direction, and for each direction we need 2 of them. And this goes with everything else. So this is true for v velocity and with w velocity. So we increase the order of equations, we increase the number of extra conditions we need to specify to solve the problem. Okay? So if I scroll down, you will see that there are a couple of things here. So, and they are given in the, unfortunately, the wrong order. So boundary conditions are, so what are the physical boundary conditions? And some of you already know what they are, and you actually proposed those boundary conditions previously, and I just said, no, not yet. But now we are talking about not only no through flow condition, W component of the velocity is equal to 0 because the fluid cannot go through the wall, so if we are considering the channel flow, right? But there is another experimental fact. It is experimental fact that under normal conditions, and by normal conditions we are talking about fluid that is considered as continuum. So which means that we consider fluid as a macro object. Do not consider its molecular structure. So at this level, microscopic level, fluid molecules get stuck to solid molecules at the wall, and they cannot move. So, and this is physics of that is quite complicated. By the physical nature of that is quite simple. It's electrostatic interaction. So molecules, when they considered at their own scales, they are polarized. So, and they are charged essentially. So different parts of molecules have different polarization, and therefore they just got stuck like two magnets. So the reason why fluid cannot slide along the solid walls is essentially electromagnetic. So molecules just get stuck because of that interaction, so attraction. Okay, so that's what happens. That is a physical condition, and this is fully consistent with what we need for to complete the set of equations, governing equations. So we need these conditions anyway, just because we have extra derivatives, and these extra derivatives require extra conditions, and physics offers us those conditions. Okay, so that's how it works. So obviously the equations that I just showed you, those equations, they are written in dimensional form, physical form. And you know that because you see density. Density appearing explicitly plus viscosity, mu, coefficient mu is called dynamic viscosity, also appearing there explicitly. As soon as you see these things, you know that the equations are physical equations, original equations, and we cannot just jump and solve them. We have to non-dimensionalize them. And how you do that, again, I'm not going to do that in detail. I just refer to pipe procedure that we went through some time ago, right? The procedure is exactly the same. You list those, all those variables, or all those physical quantities that appear explicitly or assumed to appear in the equations. For example, rho and mu appear explicitly. We also assume that the flow domain has some characteristic size, L, and we assume that velocity has its own scale, time has its own scale, and so on. So we will bring all these dimensions together, form non-dimensional groups, solve that pipe procedure problem, and we will know how many non-dimensional groups we can have. And what do you think? How many? What do you think we will have here? So let me go back to equations. So that's how they look. So, and we went through this exercise before with this part. So this was not there. but this was there. So what did we actually introduce? What extra physical quantity has been introduced? Just by looking at that. Well, that's what we had, and now that's what we have. So clearly this is new. And this contains V, X, Y, U, W, right? All these been considered previously. That's not new. That's the only thing which is new, right? So one new parameter is introduced, and therefore we need to check that, strictly speaking, but what do we expect? In the previous, when we applied the pi procedure previously, we ended up with, remember, 3 non-dimensional groups. So how many groups do you think we will have now if we proceed, just repeat this? So what's the difference? So what is the dimensional difference? So what did we introduce in terms of new parameters, physical parameters? How many? Well, mu is new, right? So it is one new. So therefore it is logical to expect that we will have one new non-dimensional group. Okay? It's just intuition, but it remains to be shown, rigorously shown, but that turns out to be the truth. So if we formally go through the procedure, we will get one more non-dimensional group, which was not considered previously. So that's something you can check on your own. And what I will do here, I will take a shortcut. Remember, once we went through procedure, pi procedure, then after that we went through the second step of scaling the equations, attributing scales, formal scales to each of the quantity, substituting them into equations, and canceling them out or multiplying through or dividing, so manipulating somehow, and then getting non-dimensional form of the equations. Remember that? So, and that's exactly what I suggest we are doing here, so I will not do it on the board, but just refer to that. So we have scales introduced for all these quantities. So U, V, and W are our original physical quantities. They have dimensions, they have units. And what we do, we will introduce this scale, and what we have denoted here by stars, it's non-dimensional quantity. So that's exactly the same as before. So is this one, so is this one, so is this one. So that does not change. Okay? And then we go ahead and substitute this into our equations. So the first one is trivial, so we have continuity equation or incompressibility, still the same equation. It contains velocity scale and the length scale, because differentiation with respect to space is equivalent to division by space, by L, by scale. So therefore the scale will be V over L, and you can see that this is a constant, right-hand side is 0, of course this will be gone, and formally the form of the continuity or incompressibility condition will not change. So that's what we do with the rest of the equations, momentum equations. I chose, for brevity, I chose to write them in a vector form rather than in a single component form. So, and if I do, then I will get this. So I will see that left-hand side contains this coefficient rho multiplied by V divided by T. So I can divide through by that, right? So if I, so I can divide through by that. And if I do, there will be a lot of cancellations. So I use the same trick as before. See, I choose T, scale for T, as scale for V divided by scale for width, except a slight change of notations. L is capital here in my notes, right? So that's the only change. Before I had a lowercase l. So everything else the same. And if I do that, so that's exactly what we've done before, we will get this type of equation. So see what happens. So remember, remember when we considered Euler's equations and we did not have any viscosity? So all the coefficients, all these non-dimensional groups magically disappeared. They all became equal to 1. And you can see that's exactly what happened here. So nothing here, nothing here. However, this time we have that extra group. And this does not disappear. Or does it? Can we actually set it to 1? Remember how we did that before? So we have the parameter and we say, well, this scale divides by this scale. So, but we don't know this one, so therefore we choose it to our convenience, and all of a sudden the result of this ratio will become equal to 1, right? Do I really have a freedom here to set this to 1? Let's just think about it. So can we change mu? Mu is viscosity. It is experimental quantity. It is the quantity which is prescribed by nature to a particular fluid. If we're going to work with this particular fluid, nature tells us, no, that's what I tell you, use it or lose it. Right? We cannot do that. We cannot change it. Same argument for density. If it is water, it is density of water and cannot be anything else. We cannot change it. Right? So neither mu or rho are changeable. L. Well, it depends on the problem. If we have experimental setup, if it is a channel, and I will consider a channel flow later on, well, the channel has the dimensions. So the gap between the plates is L. So if I want to change that, I need to break my setup, physical setup. And that is too expensive. I'm not going to do that. Right? So that is fixed. So we cannot change that. And what about V? And that's probably the biggest difference to what we had before. So remember, we were able to choose V in a particular way, so all the non-dimensional groups disappeared, all of a sudden disappeared. They became equal to 1 in the previous exercise. But that was exercise, envisaged as exercise. And we didn't really have anything which would characterize the flow. We didn't even know what sort of base flow we are looking for. We just were exploring all sorts of base flows, right? Now, let me be much more specific here. So what I will be considering next is this particular problem. So these are still two plates, and they are still placed in the gravitational field, so I still have a flow between them, right? But now I know that viscous fluid cannot slide along the top or bottom plates, right? So therefore, the velocity profile, probably hard to see for you from this distance, but it is expected to be such that velocity, all velocity components at the walls, both walls, will be 0. And if we hope that flow still happens, then clearly the maximum has to be somewhere in between, right? So if the velocity is 0 everywhere, so we have no flow. So if we assume that there is flow, and if we know that that flow must have 0 velocity at the walls, it's just physical condition. So the condition then that logically leads to the conclusion that the flow that we consider will have maximum velocity somewhere in the bulk of the channel. Is that clear? All right. If we admit to the fact that the flow has maximum velocity somewhere, so therefore this is just that is a physical conclusion. It's not a mathematical conclusion. It's a physical conclusion, physical expectation. Then this means that physically we have a scale for velocity, because that maximum gives us the characteristics of the flow. We know that maximum must exist, and this is not arbitrary, right? So therefore, V is not an arbitrary parameter anymore. It is characteristic of the flow which depends on the properties of the flow itself. So it cannot be arbitrary anymore. That's the condition, right? So that's the conclusion. That's the conclusion. And therefore, if I go back to this parametric group, this parametric group. You see that nothing can be changed. Physically, every single quantity here is fixed. It is not up to choice, up to our choice. So therefore, we will have to deal with that the way it is appears. So that was first realized by the guy known by Reynolds, 1870. So before the Rayleigh results were known. And that was introduced through Reynolds' famous experiment. Does anyone know, heard, or read about what Reynolds' experiment was about? Anyone? So Reynolds' experiment was about looking what happens within a pipe. Long glass pipe, and the water was flowing through that, pumped through that. So you can see what happens inside. And here the ink injected on one side. And the expectation was that ink would color the local patches of water, local water particles, and they will be just carried through the length of the pipe, and that will be discharged at the other end. But that's not what he saw. You saw that initially that indeed that was the case, but once the pumping rate increased, instead of going just a thread of dye going through the pipe, he saw that that line was broken and eventually completely mixed up with the surrounding fluid. So, and that's the first time people started thinking about turbulence. And the turbulence is a result of instability, because remember how we introduced instability. You expect one thing, but you see something completely different. And that was essentially a historic manifestation of instability in the pipe flow. You expect that this dye will go through the channel and leave it, but it actually, this jet or this thread of dye is broken. Okay, completely different result, qualitatively different result. So, okay, so this number is named Reynolds number, or rather this ratio here is called, so inverse of this ratio, which we see in the equation, is called Reynolds number. So, and it is turns out to be very important, and in many stability studies, many fluid flow studies, they talk about critical Reynolds number. So paying respect to the very first experiment when they see the transition from laminar flow to turbulent flow. So that happened at a certain value of the velocity. So obviously in that experiment, this is fixed, this is fixed, this is fixed, but velocity keeps increasing because of pumping rate is increasing. Okay, so Reynolds number increases, and all of a sudden you see something completely different to what you expected. Okay. So we end up with these equations. So, and what we had before was just that. Now we have this extra term, and this is shorthand notation for collection of all second derivative. It is called Laplacian, and Laplacian by definition is the sum of second order derivatives. Okay? The easiest way of defining that, of course, is in Cartesian coordinates. And we will stick with Cartesian coordinates, but the same holds for any other Cartesian coordinate system. Circular or polar coordinate systems, or spherical or cylindrical, you name it. So the expressions will be algebraically different for different coordinate systems, but the meaning will be the same. It is Laplacian. Okay. So we will follow the same footsteps as we developed before, as we suggested before. So we would like to find some solution first, and then figure out whether that solution that is observable, whether it is stable or not. So how can we do that? Well, we need to start with making reasonable assumptions. Okay? A lot of them, possibly. But at any point they have to be justifiable. So we cannot just guess the full solution, and we cannot even find the full solution in many cases, but we should be able to almost guess basic flow solution, which is a simpler, probably the simplest possible algebraic solution, but it comes essentially out of physical intuition. So, and how do we go about that? So, let me see what I have here. So, in whatever follows, I will be referring to this geometry. So, this is two parallel plates, and the fluid is pumped through parallel plates. So, before we go any further, I just want to pay attention to one fact. In order for flow to occur in a system with viscosity, with friction, you have to supply energy constantly. Or you have to force fluid constantly. Why? Well, we know why. So if you have a friction in a system, any system, does not really matter which one, any mechanical system with friction, if you do not use any sort of engine or motor or any sort of push, the motion will stop, right? So kinetic energy, which is due to object motion, will eventually be stopped, and all that kinetic energy will go to friction, to heat. So essentially what happens, if you put your hand on a table and just try to slide it, right? If you do it quite quickly, you will feel heat. So therefore, the energy of your motion is transferred to heat. And your energy, or the energy in this experiment, of course, is supplied by your muscles. And your muscles take that energy from your lunch. And if you have lunch, you can do that. If you don't have lunch, you cannot do that, right? So that's basically a very simple explanation of what is happening. So therefore, if we are talking about something happening between the plates and there is friction there, we have to assume that there is always a source of energy. It has to be constantly supplied. And that energy can be supplied in terms of force. So what sort of force do you think might be we might be able to use to maintain such a flow between two plates? So we don't put our finger in it. We don't push anything with our hands. We essentially assume that there is a pump somewhere. Remember Reynolds' experiment? He used a pump. So, and pump creates pressure head, right? Pressure is increased at one end and it is lower at the other end. So therefore that pressure gradient is what is pushing the fluid. As long as you can maintain that pressure gradient, the fluid will flow. You stop the pump and the flow will stop, right? Okay, good. So that's what we will need to keep in mind when we are talking about physical assumptions that we can and cannot make while deriving or guessing base flow. Right, so just a statement here, let me just read it. Let us look for the solution that depends only on Z. So, and here I just stated, but it should become clear for us why I'm making such a statement. We went through this exercise before. Remember, two plates, and these plates are, we assume that they are very long. We cannot see the edges. So therefore, if you close your eyes, you move along the plate, open your eyes, nothing changed. Therefore, there is no change in as you move along the plate in either x or y direction. And if this is the case, then derivative is equal to 0. Okay? So that means that any functions that we introduce can only depend on the distance between the plates, z. Okay? Is that clear? So it's the same argument as before, and I'm going through that argument very quickly. Fine. So we assume that u is a function of z, v is a function of z, w is a function of z alone. And we'll also make an assumption that obviously the simple case would be when everything is steady, which means time derivatives are gone as well. So therefore, that's what we have. But can we make the same conclusion about pressure? So if we assume that pressure does not depend on x, that means pressure here and pressure here are the same. Pressure gradient is equal to 0. If pressure gradient is equal to 0, there is no motion. We'll lose it. So we can assume that velocities do not change with x or y, but we cannot make the same conclusion about pressure. Pressure must change along the channel, and pressure must change in the direction of the flow for this flow to exist, as long as the fluid is viscous fluid. Is that clear? Okay. All right, so that is the condition here. So therefore, we can afford dp by dy being equal to 0. We might be able to justify that dp by dz is equal to 0, but we cannot justify setting dp by dx to 0. But if it is non-zero, what is the next simplest thing after 0? Constant, right? So we don't want to hurt ourselves too much by introducing anything which is extremely complicated. So yes, we know that we cannot afford 0, but we would like to, the expression will still be simple. So therefore, next simplest case is constant, but constant is not necessarily 0, definitely not 0. Is that clear? Okay, so that completes the discussion of this, and we go to the next page. So if we substitute u, which is a function of z, v as a function of z, and w as a function of z, into du by dx plus dv by dy plus dw by dz is equal to 0, that's the continuity or incompressibility equation. Clearly, you will get du by dx. We say that nothing changes in x. Gone. dv by dy, we say that nothing changes in y. Disappeared. So the only other term left would be dw by dz. So dw by dz, but the right-hand side of this equation would be 0. So dw by dz is equal to 0. What does that mean? It's constant. But what is, if it is a constant, it has to be the same in the bulk and at the boundaries. But we know what it is on the boundaries. 0. So therefore, w must be equal to 0. So we obtain this, we conclude that flow cannot occur across the channel, only along the channel. Okay? So that's what we arrive at. Okay, so then we use the equations that we derived previously, written in a component form, and get rid of all x derivatives, get rid of all y derivatives, and keep only z derivatives. And keep in mind that w is 0, got to be 0. And that's what we are left with. We also keep in mind that this bit here cannot be 0. Right? This cannot be, because if we lose it, that's it. We'll lose the driving force, so no flow will be there. So physically, this is impossible. So therefore, that's the situation. So therefore, because this is a constant, I just give it a name, pi. So it is pressure gradient. I call it pi, constant. Okay? And from here, I will get this condition. dp by dx is equal to pi is equal to constant. So that means, so remember that this is an equation which has to be balanced, right? So, and if it is a constant, and if it is something else, you're adding apples and oranges, right? That cannot happen. So therefore, the second derivative of u with respect to z must be 0. Or it must be constant, sorry. Agree? What sort of function satisfies this condition? Second derivative becomes constant. Parabola, quadratic parabola. So without any solution, we already know that u must be parabolic. It has to have zeros at both ends, both plates, and it has a vertex somewhere in between, and we know from symmetry it will be exactly dead in the middle. And that's where the velocity will reach its maximum. So pretty much that's what we expect to do without almost any algebra. We do need to know that second derivative is equal to constant for a parabolic function. That's probably the only mathematical thing we need to have here. All right, and that's what will happen with equation in y direction, span-wise direction. But we assume that we can choose the direction of pressure gradient. So we just say that pressure gradient is in x direction. Why? Because if it is not in x direction, we can always turn. Right? So if we have no boundaries, no edges, we cannot any edges, we can always turn my coordinate system and we will not see any change. Right? So we can align x direction with the direction of the applied pressure gradient. And that's what this means. So in that case, by construction, dp by dy is equal to 0. So therefore, this second derivative of z, of v, must be equal to 0. So second derivative of a function is equal to 0. What sort of function is that? Linear, right? But that linear function has to be 0 at the bottom plate and at the top plate. It can only be achieved if both a and b are equal to 0. So if a and b are equal to 0, what happens? The whole expression for v becomes 0. So v disappears. So we only have u, which is parabolic, but v is equal to 0 because of our discussion. And w was equal to 0 for a long time already from the very beginning. So therefore only u component survives. And dp by dx must be a constant. So this is the conditions under which we can create this flow and maintain this flow, steady flow. Such a flow has a name, plane Poiseuille flow. Okay? Many of you, of course, are well familiar with this. So, in more detail, if I have this equation, so remember the equation was 1 over Reynolds number of the multiplied by the second derivative is equal to pressure gradient, which is pi, or negative of that. So I just rearrange that and put Reynolds number here, so multiply it through. So this is my equation. And then, of course, I solve it. When I solve it, I will get my parabola. So that's just the analytic expression, algebraic expression. So here we go. And the maximum of that, of course, is when z is in the middle. So one more thing I chose to do for convenience, which is different to what we discussed before, slightly different to discuss before. I assumed this. So the plates are separated by distance 2L. See? Plates are located at z equals capital L and z equals minus capital L. So, and in that case, non-dimensionally, I will have the domain which is not between 0 or between minus 1/2 and 1/2, but rather between minus 1 and 1. Okay, it's just more convenient for us to write 1 rather than 1/2. Okay. So, all good so far. We got our equation. Here we go. And from here we will be able to find the pressure gradient. So, but how? How do we find the pressure gradient? Okay. So, maximum expression here, maximum of this expression, will be achieved at z equals 0. And it will be equal to Reynolds multiplied by P divided by 2. Okay? So clearly, is it clear why maximum is at z equals 0? It's quite clear. So because if z is not equal to 0, then you subtract it from 1. You make it smaller, right? So z equals 0 is obvious maximum. So remember that at this stage, we just said that there is a characteristic scale. And that characteristic scale is the maximum velocity, right? Physical velocity, dimensional velocity. So if I use maximum velocity, maximum possible velocity as the scale, so non-dimensionally, what is the maximum? 1, right? So essentially, well, that's an important thing to understand, and just make sure that you do understand that. So at this stage we said, well, let's assume that maximum velocity is the scale chosen for this problem, velocity scale chosen for this problem. Fine, we go through the algebra and we don't pay attention to the fact until this very moment. And at this very moment we say, all right, hang on, we got some expression for our non-dimensional velocity. Here it is. I know that it has a maximum at z equals 0. So, but according to this, I will get Reynolds divided by 2 multiplied by pi. But because I chose the scale in such a way that the maximum must become 1, so essentially I have a condition which relates Reynolds number and pressure gradient. So pressure gradient essentially defines Reynolds number. That's what that means. So, and therefore, that's what I will get from here. So I know that the Reynolds number multiplied by pi divided by 2 has to be equal to 1. And from here, I see this relationship between pressure gradient, non-dimensional pressure gradient, and the Reynolds number. Is that clear? Good. Okay. Well, what's next? Well, what's next is, again, well familiar to us. We would like to know that whether we can actually observe this flow. We know how it looks. It is non-trivial. It is parabolic. So it is observable in some cases, but according to Reynolds, at some cases, at some regimes, it might break down. Okay, so it might disappear. Okay, so let's go back to Reynolds experiment. So what do you think happens there? So why this thread of dye becomes blurred? How can it happen? So what physically happens there? So perturbations, but what do they do? So what sort of perturbations? So remember, base flow is just longitudinal flow. The flow occurs in one direction. Only u is non-zero. But if only u is non-zero, then any particle will be going along the straight line. And if it goes along the straight line, it will eventually exit the channel, and that's it. But that's not what happens in experiment. In experiment, the particles start fluctuating, going up and down. So which means that velocities perpendicular to the base flow velocity are excited, right? So that's what perturbations mean. So therefore, we should assume that in some conditions, perturbations will have all three components, u prime, v prime, and w prime. So therefore, we must make a conclusion, logical conclusion, that at some point, velocities other than u velocities will appear. Is that clear? Here we go. So here we go. And again, I do not spend too much time on that because we went through this procedure again. So you simply write your solution as a sum. U bar, which is our quantity that we just defined, base flow, plus all sorts of perturbations. And if you do that, you will get these equations. You will see that these nonlinear terms when perturbations are multiplied by perturbations. See that? So what we will do, we will linearize this system as we did before. So essentially what we will do, we will push all these nonlinear terms somewhere to the right-hand side, and keep all the linear terms which have perturbations only as perturbations, not multiplied by themselves, in the left-hand side. So that is very quickly, and this is exactly the same as we did before. Remember? So algebraically, no difference. Just more terms to deal with, but ideologically, phenomenologically, procedurally, it's all the same. That's what we will get as a result of that. Okay? So I do not go through details of that because we've seen that before. So all linear terms are collected on the left, and all the nonlinear terms are pushed to the right-hand side. We've seen that before. Okay? The only difference is that we have a whole lot of new terms, well, all multiplied by 1 over Reynolds number. So that's the only difference. Now, all these perturbations, they are still perturbations for the same fluid and in the same system. So therefore, what can you say about velocity perturbations at the walls? They must be zero, right? Because whether this is perturbed velocity or whether it is base flow velocity, it's still physically, it is a velocity, and velocity, physical velocity, must be zero at the boundaries. Okay, so therefore they have their natural boundary conditions the same as base flow conditions. So standard conclusion is that if these perturbations are small, then right-hand side can be neglected. Right? If u is small, u times u prime is small, u prime times u prime is even smaller. Get rid of that. Then all quantities are written in this form, and we've seen how it is done before. Right? So we have these quantities that describe variation across the channel, and we have the quantity which describe variation in x direction, variation in y direction, and variation in time. All the same. So this is completely standard, and this is no different whether you consider fluid flow problem or any other physical problem. So it's all the same. So algebraically it is the same procedure, same pretty much outcomes. So mathematically it is all the same. It is standard. So if we substitute things in, we will get that. That is the system of equations we get, and we've seen it before, except we didn't have any of those. Okay? So this was there, this was there, this was there, this was not. So that's the only thing which is being added. Okay? So, good. We were encouraged to do something with these equations to simplify them. And we came up with quite a few interesting conclusions about the perturbations being two-dimensional when we considered inviscid case. So now we have extra terms, but we still tempted to do the same. So it's just temptation. So we did well in the past. Why don't we try to do it again? And that's what I've done here. So I introduce exactly the same transformation. So remember alpha tilde. So I take the first equation multiplied by alpha, take the second equation multiplied by beta, add them together, and that's what I will get as a result. Again, the only difference is that I will have these extra terms. Okay, so I don't go through the algebra. I'll leave it up to you if you are interested, but hopefully it is quite clear what I'm doing algebraically, right? So if the need be, you will be able to do it on your own. So the main thing is from now on for you to understand, not necessarily do the algebra, but understand what the procedure is. The procedure is the same. So, all right, we have that. So, now I'm referencing equation 3. Let me just see where it is. So that is equation 3 is equation for the W, for cross-channel velocity, right? So I do something else here. Okay. So I also introduced this transformation for sigma, and it is exactly the same as before. This is transformation for pressure, which is exactly the same as before. So see, it's all the same. It's all the same. But there is one more thing I do. Look, I have at this parameter 1 over Reynolds number appearing in my equations, and I redefine it this way. Okay? So, and why do I do that? Because that's the combination which you will end up with if you do that business with multiplying things by alpha and adding things together. So that's what will happen. Okay? All right. That's what we have. So that's what will happen with the W equation. And that's what the equation for continuity or incompressibility is going to look like. Now, this is telling. You see that initially we had 3 terms added together, and now we are left with 2. Right? So it is tempting to conclude that we might be able to live with a 2-dimensional problem again. It looks like the problem becomes algebraically 2-dimensional. Right? One of the terms disappears, it gets collapsed. We need to be a little bit careful here. So, 3D problem is reduced to an equivalent 2-dimensional problem, as you can see here from just one of the variables of the velocity components disappeared. And if you compare what we got here with what we started with, so that's our starting point. So if we choose, if we consider this, and if we choose beta equal to 0, and if we choose v equal to 0, so then see what happens. So if beta is equal to 0 and v is equal to 0, what happens to this equation? The second equation disappears completely. Agree? All right. And this term disappears as well. So therefore, one equation disappears and one term disappears from the continuity equation. So therefore, we will get something which looks exactly as we have here. Right? So that's why this problem here is called equivalent 2-dimensional problem, because it looks like 2-dimensional problem, and it could be formally obtained by simply forcing beta to be 0 and v being 0. Okay? All right. So where to from here? So let us have a closer look at the expression for sigma r. So tilde and non-tilde. So that's the relationship between them. So this is the quantity which characterizes the growth rate. Okay? So by looking at this, what can you say about sigma r tilde and sigma r? Well, it's clear, right? It's written there. Because this coefficient here is definitely greater than 1. Agree? Okay. So how do we interpret this? Well, another trivial observation is here. So if sigma r is equal to 0, then sigma r tilde is also equal to 0, right? So that's trivial. So therefore, if we are at the border of stability, sigma r is equal to 0. So no matter whether it is 2-dimensional, 3-dimensional, so tilde, non-tilde, it is still 0. Agree? Okay, good. logical conclusion, and you need to think about it. So I have it written here, and it is correct, but if you read it for the first time, you might not quite get it. So that's was my own experience when I saw these type of statements for the first time. You might need to stare at it for a while, and maybe outside of this class to actually absorb that, to start feeling what is happening. So if the critical condition sigma r equal to 0 is achieved for three-dimensional problem at some critical value of Reynolds number. Okay, so what do I mean by that? So I'm honestly solving stability problem in three-dimensional case. I increase my Reynolds number at some point after a lot of sweating, so I solved three-dimensional problem, right? So a lot of work. I solved it and I found where the instability occurs. So this thread of die starts breaking, right? I found it, so somehow I found it. And this happens at this value. Then the same critical regime occurs in two-dimensional problem at Reynolds number tilde, which is related to the three-dimensional value like that. Where did it come from? Well, it comes from just definition of all these quantities. So that comes from our equation, so we just introduced this. But Reynolds tilde quantity and no tilde quantities, they are related, so they are physically relatable. So one is three-dimensional, one is two-dimensional. That's what their physical meaning is. So, once again, if we put a lot of effort and solve three-dimensional problem, then two-dimensional problem, which will give us exactly the same result, zero result, right? Because if three-dimensional sigma is equal to 0, then two-dimensional sigma is also equal to 0, just algebraically, right? Then that would mean that similar two-dimensional result is obtained at this quantity, at this Reynolds number in two-dimensional case. So this is three-dimensional, this is this is three-dimensional, this is two-dimensional. So you see that you take three-dimensional Reynolds number and multiply by this coefficient. Remember that alpha tilde is alpha plus beta, so it is larger than alpha. So therefore this coefficient is necessarily less than 1. So therefore the conclusion is, so it goes slightly different to what we had before. The conclusion is that if we solve the problem and we found critical Reynolds number at which three-dimensional flow becomes unstable, that means that much before or early before that, two-dimensional flow became unstable already. So you wasted your time, you wasted your effort to find the three-dimensional transition, while two-dimensional transition happened long time before. So practical conclusion, don't bother. Don't bother solving a three-dimensional problem. You will not be able to get critical Reynolds number as far as physical system is concerned. Because whether the flow is three-dimensional or two-dimensional, right? This is our definition, subjective definition. Nature will do what it needs to do, what it wants to do. And it does not know whether what it does is two or three-dimensional. It just lives its own life. And it doesn't care about us, whether we do it, whether we call it three-dimensional or two-dimensional. That just does its own things. So therefore, if we insist on suffering and trying to study three-dimensional problem, well, it's your business. If you love suffering, so some people do, so go ahead, be my guest. But you're wasting your time because physics does not require that. Physics tells you that two-dimensional consideration will give you the right answer. And three-dimensional consideration will not give you the right answer, even if it is more expensive. Is that clear? So this is called Squire's theorem for viscous fluids. So before we introduce Squire's theorem for inviscid fluid, here we get the same physical conclusion that two-dimensional perturbations are more unstable than three-dimensional ones, but now this is for much more realistic case of viscous fluid. Okay? So that is the main conclusion that we draw from here. Okay, so far it was all qualitative. And now we need to get to actually things known as computations, right? And as I promised to you, so I will do that in a way which is not a historic way, but rather practical, contemporary way. So, and introduction of stream function is not used anymore, because stream function has a lot of limitations. So the stream function is suitable for, thank you, for simple problems, relatively simple problems, definitely only two-dimensional problems, but the method which I will show you here is equally valid for two-dimensional, three-dimensional, and whatever exotic cases you might have mentioned. So it is absolutely general, robust, and will work no matter what sort of problem you are solving. But I will demonstrate it on a two-dimensional problem, essentially. That's what I do. It's just because we have limited time, and the only thing we have to time for is covering the simplest case, so two-dimensional case. All right. So what we have is, so we have Reynolds number. We have some sort of critical Reynolds number, and on the left, the flow is base flow. That parabola is stable. We will be able to observe this parabolic flow. If we cross this border here, then we definitely know that perturbations will introduce all perturbations, vertical perturbations and horizontal perturbations, and that thread of dye will be washed away. Well, it will be just essentially blurred. Okay, that's what we have. So that's what happens on the diagram. Let us, so we, how many, just a couple of minutes left, probably? 2 minutes. So I will just make just general non-algebraic conclusion, and then tomorrow we will consider this in more detail, and this will naturally lead us to considering to nonlinear analysis. So we're sort of on schedule. So we consider details of how we can actually compute this value. So all we know that at this value, that the critical value, sigma r growth rate is equal to 0. It is negative here, it is positive here, here it is 0. So we need to know how to find it. Okay, so, and the way to do that is to consider our two-dimensional equations, but write them in a matrix form. And this is the matrix form as it will appear. I will not discuss it, the details of that today, but that's what our goal is. So I'll just introduce some general concepts here, and then we will stop. So equations will be written in this form, matrix form. So what all those elements are, I will discuss them tomorrow. But then we also introduce an important generalizing notation, operator L sigma alpha, this one. And it will contain matrices. It's essentially a sum of matrices. And linear stability problem then will be formally written like that, where W represents the vector of U, W, and P. So this W vector contains of velocity components U and W, along channel, across the channel, and pressure. Okay? So that's what we will be dealing with. This will be the starting point for tomorrow. So, and my first thing will be to discuss how this is read from the equations, from the original equations. Okay? All right, I'm done for today in terms of my lectures, but if you had a chance to look through the lecture notes on derivation of Navier-Stokes equations, and if you have any questions, or if you have any other questions about, say, algebraic steps that I ask you to go through today, any other questions about the subject, about life, about anything you want to discuss, I'm happy to stay and we can talk, so up to you. Please speak up because I'm sort of...
We consider the velocity you need at the state velocity is a concern of jet. So you have to y. So if you consider v equal to jet, v equals v net equal to 0, w jet equal to 0, then the same Squire theorem again.
If we have parallel flow, basic parallel flow, like we have u velocity, which base flow, which where we have a unidirectional flow, so flow occurs in one direction, but it is the velocity changes with the depth, right? So only one velocity at the base level going in a certain direction, so no left, no right, just straight. But how fast you go at the bottom, in the middle, and at the top will be different, right? So in this case, it is sufficient to consider perturbations only in the direction of the primary motion, right? So what you will see that the perturbation will occur in the direction of the main motion and across it, but not in a plane. So therefore, if I'm going that way, and I'm going straight, so once perturbations are developed, I will not be going straight, I will be going like that. Right, so I'm going up and down, but generally in the same direction, but I will not drift sideways. Okay, that's what it means. So I'm going straight, that's base flow. If I'm perturbed base flow, so something went wrong with my head, so I'm going like that, like an idiot, right? But I'm not complete idiot, I will not go like that, I'm not drunk. Okay, so that's what the Squire's theorem is about. That's what it does. Okay, so it tells me that, yeah, you're getting a little bit mad, but not necessarily drunk. Anything else? Yeah, sure.
So while we were deriving the quadratic equations, after the while we were dealing with the base flows, while we were deriving the base flows, so what we considered was the pressure gradient along the axial direction. We considered it to be constant. And as per our setup, we have infinitely large plates, and the height, the distance between the two plates can be considered to be finite. So why not we consider del P del Z as constant?
Yes, we do.
It cannot be constant. It has to be zero, because if I go back to the equations, right? So let me see. So I'll refer to this equation here. So it's a physical system, but we will just, it will be the same whether you're dealing with physical or non-dimensional system. So what we already know, that u is not 0 and u is a function of z alone. We also concluded that v is equal to 0. We also concluded that w is equal to 0, right? So let's go through what we have here. So w is equal to 0. So this is 0. 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 dp by dz must be 0. It's not our choice. It's just part of the equation. That's what happens. If we assume that there is no cross flow the pressure gradient must be equal to 0 in that direction. So it's not an assumption, it is a rigorous conclusion. So now, I have to emphasize that this pressure here, you see that gravity is not present. And the reason why I didn't put the gravity in, because I assume that it is already absorbed. It is sitting inside. If I had a gravity term written explicitly, hydrostatic term, then we would get variation, linear variation with the depth. We would have G multiplied by Z. Pressure will be rho multiplied by G multiplied by Z. As we all know, that's hydrostatic component. So the deeper you go, the higher the pressure, right? But in this case, just not to bother with writing extra terms, just mechanically writing extra terms, I will absorb it there. It's sitting inside, so it is there, but we cannot see it. It's my laziness. I don't want to write too many things. Anything else? Okay, think about any questions. So, as I said, I'm always open for answering questions in any break, in the break between the lectures, lunch break, before lectures, after lectures. So, if you have any questions, please do not hesitate to ask. And today I skipped a lot of details, so they are in the lecture notes. So please go through those lecture notes. So read through them. You will see that there are a few interesting things you might pick up from there. So usually I know that derivation of Navier-Stokes equations is not easy. It's not easy. If you do it properly, rigorously, then students just cry. You know, if you, I tried that. I tried that, and students just, well, look at you like you're just torturing them, right? So too much, and therefore I ended up with just a formula when I tell students what physically happens. If you can understand the physical concept, if you can accept the physical concept or physical reasoning behind the mathematics, then mathematics, you will be able to follow it up. So you just take a book and you will read the book and you will understand what is happening as long as you know the physics behind.